All right, here's a practice question for a first order circuit. Okay. What do we got going on here? Well, we have a capacitor and a voltage source and a couple resistors. Got that middle switch flipping. So, first we need to figure out two things. Voltage is a function of time across the capacitor and current across the time across that resistor. And we are going to find that first. Let us solve for the circuit for t less than 0. So that's going to be all values of for time less than 0. So this is before that switch comes down. Let me redraw the circuit really quick. Okay, we redrew the circuit for t less than 0. And what I did was I got rid of the switch in the picture because it kind of confuses the drawing a little. And we can easily see when this is open, this current travels, across this resistor and that resistor, the one underneath it. It's not obviously going to go through that open area. So you can simply redraw it as this to make it look easier on the eyes. And we really need to figure out the initial voltage across the capacitor, to figure out what we're starting with as voltage degrades over time, what we're going to start with as it starts to change, which the change will be when this resistor is taken out, is what it seems. I'll go into detail about that after, but let's first find the initial voltage across this capacitor. That's going to be from this top point to this bottom point. That will be the initial voltage across the capacitor. And the reason behind that is, let's say, for example, we redraw it really quickly. And then we have, let's make the capacitor open like this, right? From this point A to B, what is the voltage across that? Well, as it comes to ground, which is right here, as you travel from point A to B, which is to ground, the next thing closest to ground, you pass through those two resistors. And those two resistors are going to have voltage drops across them. And that voltage will be the voltage across the capacitor. So that will be what's on the capacitor. So technically you could combine these resistors and make them 30, and then just find the initial voltage across that 30 ohm resistor. That'll be your answer. So how are we going to solve that? Well, we know voltage is equal to R times I. Take the initial, the main voltage, right? We know as it sits for a very long time, I forgot to mention this. This capacitor, we always assume that it's sat for a very long time, is an open circuit, right? So we can just solve this circuit as a single series circuit. So we can do the voltage, the initial voltage, which is 50, divide that resistance over the total resistance. Since they're all in series, we can add them together. So 20 plus 10 plus 20, 50K. You don't have to put 50K if you don't want to, as long as at the end, let's say 1, you add the milliamp. Why milli? Because it's in killi, and it'll make it in milli. Kind of like the opposite end of the unit. K is 10 to the 3, milli is 10 to the negative 3. Obviously, you can see how I did that, because since it's on the bottom, right, you're going to have 50,000. You're going to end up with like 0.00001, but it makes it faster to know since you're dividing by kilo. You can just make it milli on the other side. It's more of a memory thing, but you get 1 milliamp. That's going through this whole circuit. So 1 milliamp we know current times resistance is voltage. So if we do 1 milliamp times 30 kiloohms, we can just do 30 times 1. That gives us 30 volts. That is our initial voltage across the capacitor. Nice. So now that we have our initial value, I can now solve the next part of the circuit for t greater than 0. And I'm going to all right, so this is what we have here, right? So we have for t greater than 0. So now we need to figure out what is the final voltage that it's approaching. Obviously, we need to figure that out because the voltage here is still present, right? It's not going to approach 0. So the voltage across that 20 kilo ohm resistor will be the voltage that it approaches. So we can do 50 volts divided by 40 kilo ohms, and that gives us divided by 1.25 milliamps. Yeah. And that times 20 kilo ohms, because that current's going through here, right? Because this is an open as it goes to infinity. So we get 25 volts. Oh, that makes sense. They're equivalent resistance, so it's going to cut it in half. Okay. So we know that V final is 25 volts. Okay. So what does that mean? So the formula that you actually use for first order circuits is V final plus V final minus V initial e to the 1 over 2 RC negative times T, right? And that is for all the equations for first order. That's how you solve all of the capacitor ones. This changes for the inductor. Okay, so for our equation, so we end with 25, start with 30. So let's see what we got here. So we end with 25, right? 25 plus 25 minus V1 is 25 minus 30 is negative 5. So we get negative 5 e to the negative 1 over 2 RC T. And this is the formula. I can show you how to get the e here in a second. But, so say we start off at t equals 0, right? This will be, no. One second. I had it backwards. V initial minus V final. And that makes sense. I definitely knew something was wrong. Because this has to be 30 when t is 0. Because that's what it starts at, 30. That's its initial value. If this is 0, right, it's going to be e to the 0, which is 1. And that'll be just a 5 there. So it's 25 plus 5. That gives us 30. That checks out. That's good. That's what we want to see. So now we need to find our E. So I can kind of explain in a little more detail if you want to derive that. You would do a source transformation there. Let me go on another page. Okay, and I just drew a fresh one so I can start from scratch. So I'm going to do a source transformation so I can make this look better. And the only reason I'm doing a source transformation is by doing a KCL at this node up top, I can prove that that's how you that you get the equation I have up top, e to the 1 over 2 RC. So this becomes, by source transformation, you do the voltage divided by the resistor in series with that voltage source, which is the 20 kilo ohm, and that gives me 0.25 milliamps, and that resistor becomes in parallel with this source, which is 20 kilo ohms. Okay, now KCL this node. We find that those two resistors are in parallel, so 1 over 20 plus 1 over, it's going to be 10, obviously. If you grab the reciprocal, 0.1, we get 10, right? 10 kilo ohms. So we could redraw that as so. This drawing is not it. Not my best, but it will work. And then we have the capacitor. Okay. KCL. Well, what is current for a capacitor equal? It's equal to C dV dt. What is current for a resistor equal? It's equal to plus V over R. We're doing a KCL. We know that voltage is equal to R over I, or times I. Divide the R over, we got an I. And that current source is coming in, we get minus 0.25 milliamps. Okay. It's equal to 0. Plus the 0.25 over, you get C dV dt plus V over R is equal to 0.25 milliamps. Okay, we have this constant over here. What do we do about that? We can really just get rid of it. It's irrelevant in this state. For a differential equation, if you have a constant on the right side, just for this case, it's irrelevant. We don't want the constant here. Equal to 0. And we have this equation here. And the resistor is the dampening factor, is what it's called. Divide everything by C and you have 1 over RC, right? And then as you, as you solve the equation, if you do the following, V is equal to E to the MT, dV dt will equal to ME to the MT. And this would really, if you replace everything, it's M plus 1 over RC. M is equal to negative 1 over RC. And I am wrong. There's no 2 there. That's why it's good to check. For this circuit, it's 1 over RC. My bad. So you can plug in that answer, RC. Resistance seen is 10,000 times 0.1 times 10 raised to the negative 6. 1 divided by that number, we get 1,000. So 25 plus 5 e to the negative 1,000 t is equal to voltage as a function of time across the capacitor. And that's the voltage basically all up here. And if you want to find the current for the resistor, well, what do we know about current? Current is equal to the following. Divide the R over the resistance by that resistor, and we get the current for the resistor. So divide this all by 20,000, or you could do 20K, whatever you want to write. And that becomes the current across the resistor as a function of time. And there you go. That is that.